and welcome to Tvaritam AI. In this video, we will discuss neural networks. A neural network is essentially a function approximator. This means it can learn to approximate almost any complex relationship between inputs and outputs, even the highly nonlinear ones. Unlike simpler machine learning models like linear regression, neural networks are highly flexible. This flexibility allows them to model very complex patterns, but it also makes them more complex to train. Because of this, they come with many hyperparameters, things like number of neurons, number of layers, learning rate, activation functions, which needs to be tuned carefully. Now, for a basic architecture of a neural network, it is made up of three main type of layers. First is the input layer. This is where we feed the raw data into the model. Each feature of the dataset corresponds to one neuron in the input layer. Second is the hidden layers. These are the core of the neural network, and all the learning and transformation happens here. Third and last is the output layer that produces the final prediction, whether it's a number in case of regression or a class label in case of classification. Now for hidden layers, these are the layers between input and output layers, and they are called hidden because their outputs are not directly visible. They are the intermediate transformations. Each hidden layer transforms the data into a new representation, and early layers usually capture simple patterns, for example basic relationship or simple combination of features, while deeper layers can capture more complex abstractions from the data, for example interaction between the features and higher level patterns. This is called hierarchical representation learning, where each layer builds on the previous one. Now in practice, 1 to 3 hidden layers are usually enough for structured tabular data. It helps to train faster and provides a good baseline. For complex relationships, 4 to 6 layers can be used. It can provide better feature extraction but requires more data and careful tuning. More than 6 layers is usually an overkill for tabular data and can easily lead to overfitting. They are mostly utilized for image or textual data. Now when it comes to units or neurons, they are the smallest computational element in a neural network. Each neuron performs 3 main steps. It takes the input, multiplies them by weights and adds a bias, and passes the result through an activation function. Each neuron learns a small piece of overall pattern, and together all neurons in all layers learns the full mapping. More neurons per layer increases the capacity of a single layer and allows the network to capture more variations in the data. But too many can lead to overfitting. Now one should start small and increase the number of neurons gradually based on the validation performance. Now when it comes to relationship between depth and width, depth is the number of layers in the network. More layers mean deeper network, and width is the number of neurons in each layer. So high number of neurons will contribute to a wider layer. Now depth and width are not independent of each other. Deeper networks use narrow layers, while shallow networks may need wider layers. Total parameter count matters more than specific configuration. For structured data, a wide and shallow architecture often performs better than a very deep network, and to decide the number of hidden layers and units, there is no fixed rule. Usually, we start with a simple 2 to 3 layers and we add more layers or neurons only if the model is underfitting. Too many layers or neurons can make the model memorize instead of generalize, and we should always evaluate performance on unseen data before increasing the complexity. Now that we have understand the structure of neural networks, let's talk about one of the most important components of a neural network, and that is the activation function. An activation function is a mathematical function applied to the output of each neuron. Its primary role is to introduce nonlinearity into the network. Without it, no matter how many layers we stack, the entire network would behave like a simple linear model. Non-linearity is what allows neural networks to learn complex relationships, patterns, and interactions in the data. The most commonly used activation function today is ReLU, or rectified linear unit. It simply outputs 0 if the input is negative and the input itself if it is positive. And why it is very popular? Because it is computationally very efficient. It helps in faster training, and it significantly reduces the vanishing gradient problem compared to older functions like sigmoid and tanh, which we will discuss shortly. However, ReLU also has its limitations, which is that it has a dying ReLU problem where neurons can get stuck permanently outputting 0 and stop contributing to learning. It also produces outputs that are not centered around 0. For this, we have a leaky ReLU solution, which is another activation function that solves the dying ReLU problem. The idea is that instead of outputting a hard 0 for negative inputs, it outputs a small negative value. This keeps a tiny gradient flowing even when the input is negative, and this prevents neurons from dying and maintains gradient flow throughout the training. Now next is sigmoid function. It maps any input value to a range between 0 and 1, that also we have discussed in logistic regression video, and it is useful for probability interpretation and binary classification, mostly utilized in the output layer also. However, sigmoid has some serious limitations as it suffers from vanishing gradient problem, meaning gradient becomes extremely small during backpropagation and learning slows down. It also produces outputs that are not zero centered, which can slower convergence during training. Now for tanh, which is another activation function, it maps values between -1 and 1. The key advantage here is that output is zero centered, which leads to better gradient flow compared to sigmoid. However, tanh can still suffer from vanishing gradients, particularly in very deep networks. Hence, sigmoid and tanh, because of the vanishing gradient issue, are not the first choice when it comes to deep learning nowadays. ReLU is the default that most people go for. Now, for activation functions in the output layer, these depend entirely on the type of problem you are solving. So for binary classification, we use sigmoid. It gives us a probability between 0 and 1 for two classes. For multi-class classification, we use softmax. It converts the outputs into probabilities that sum to 1 across all classes. For regression, we use a linear activation function, meaning no transformation is applied and the output can take any real value. And in special cases, we use tanh when the output needs to be between -1 and 1, or ReLU when the output must be a non-negative number. Now let us discuss weight initialization. Weight initialization is the process of setting the starting values of weights and biases before training a neural networks. Neural networks need random weight initialization because identical weights make all neurons learn the same feature, which causes a symmetry problem. So the network cannot learn diverse patterns. As compared to linear regression, they don't have this issue since there is no hidden layer symmetry in a linear regression model. But for neural networks, we cannot assign same weights and biases to all the neurons. So now talking about the types of initialization method that we use. First is uniform initialization, and here weights are simply sampled from a uniform distribution, meaning every value within the range has an equal chance of being selected. And this range, as you can see, from -a to a, this is usually a small number. Then normal initialization, here weights are sampled from a normal or a Gaussian distribution. It's a bell-shaped curve if you look for the graph, and it is centered at 0. When it comes to other methods of initializing weight, we have Hay or K-means initialization. This initialization is specifically designed for ReLU based networks because ReLU zeroes out all negative values. Roughly half the neurons are inactive at any given time. And here what we do, that weights are sampled from a normal distribution with standard deviation. So if you are going for a normal version, the second one, you see this is the range between 0 to 2 divided by n number of input units standard deviation. And when we are going for a uniform distribution, it is negative under root of 6 divided by the number of input units to under root 6 again divided by number of input units. So Hay initialization can also have a uniform version and a normal version where we use n in, which is the number of input units. When it comes to Javier initialization, which is more useful for sigmoid and tanh activation functions, here the goal is to keep the variance of activation stable as signal moves throughout the layers, and the weights are sampled either again from a uniform distribution or from a normal distribution. Here we also consider the output units or number of output neurons in the layer 2. So here the formula is similar, but if you compare, you see we divided by not just n in, but also by the number of output units. Now moving forward with the loss function, when it comes to loss in terms of regression, we go with mean squared error, which penalizes large errors more heavily, and it is useful when large deviations are undesirable. Mean absolute error treats all errors equally and is more robust to outliers, but as a default for regression problem, mean squared error is a better approach, given the fact that in a lot of scenarios we want to punish large deviations more. Classification loss functions are similar to what we have in logistic regression. So binary cross entropy, that is used for binary classification, and categorical cross entropy, that is used for multi-class problem. Now for regularization, where we want to prevent our models from overfitting so that our model does not memorize the training data but instead learns the patterns so it can generalize on new or unseen data. First is L2 regularization, also called rich, and it adds a penalty proportional to the square of weights. This encourages the model to keep weights small and discourages overly complex solutions. Second is L1 regularization, also called lasso. It adds a penalty proportional to the absolute value of weights. This can actually drive some weights to zero, effectively performing feature selection in some scenarios. Now L2 and L1 behave similarly as they behave for linear regression or a logistic regression model. Additionally, we have a dropout regularization for neural networks. Now this is a very effective technique, and the idea is to randomly turn off a certain percentage of neurons during training. Now it is not the same neurons that are turned off every time. For each epoch, meaning full pass, so epoch is a full pass through the training data, a different random subset of neurons is disabled based on the probability value that we set, something like 0.2 or 0.3. So no neuron is permanently disabled. Every neuron gets trained, just not in every single pass. So we train multiple epochs, and in every epoch we randomly turn off a certain percentage of neurons. This forces the network to not rely too heavily on any neuron and instead learn more robust and distributed representations. Now let us talk about backpropagation, and this is an important part of a neural network. And this is responsible for how we minimize the error in our algorithm. So what is backpropagation? After the network makes a prediction, we compare it to the actual value, calculate the error using the loss function. Backpropagation is the process of taking that error and trying to understand for every single weight in the network how much did that weight contribute to the error and in which direction should it be adjusted to reduce that error. Now how does this work? There is something in mathematics or calculus known as chain rule. So a neural network is a chain of operation. Input goes through layer 1, then layer 2, then layer 3. So there are hidden layers and then the output layer at the end. So each operation depends on the layer before it, and the chain rule lets us calculate how a change in any one weight affects the final loss, even if that weight is many layers away from the output. So to understand this process step by step, the first step is that we start at the output layer where our loss is calculated. We already know the loss here. We calculate how sensitive the loss is to the output, which is our first gradient. Second step is to move one layer back. So using the chain rule, we compute how sensitive the output was to the activation in previous layer, then how sensitive those activation were to the weight in that layer. Multiply these together and we get the gradient with respect to those weights. Then we keep going backward layer by layer all the way back to the first layer. At each step, we are multiplying gradients together using a chain rule. We now have a gradient for every weight. Each gradient tells us two things: the direction to adjust the weight, which is the sign, and how large that adjustment should be, which is the magnitude. And then we update the weight, and optimization algorithms like gradient descent is used. And these gradients, we use the gradient to update every weight in the network, making them in a direction that reduces the loss. Now this works well because each weight update, however small it may be, making the network slightly better at its prediction. When we repeat this process again and again across many epochs, the network gradually learns the pattern in the data. One thing we need to be aware about is that if gradients get very small, as we go back through many layers, this is the vanishing gradient problem, because this makes the learning very slow as weights are barely updated. And then learning almost stops. This is also one of the reasons why good activation function and proper weight initialization, as we discussed in the previous part, are important. Now, one thing to mention here is that if you do not understand backpropagation or chain rule in detail, you can also refer to the backpropagation video where we can go a little bit deeper into how chain rule works in calculus. Now, talking about the full training pipeline of a neural network and how it works, first step is we initialize the weight using the technique that we have discussed in the weight initialization section. Random values for W and B, and then we have a forward pass, which is the input data passed through all the layers and network generates the prediction. Then we compute the loss and compare the predictions against the actual values using the loss function. This could be a mean squared error or something similar for classification problems. Then we do backpropagation, where chain rule is used to compute the gradient of the loss with respect to every weight. And last is we update these weights using an optimization algorithm like gradient descent. And we repeat this until convergence, not the weight initialization that only happens once at the very beginning, but the other 4 steps are repeated in every epoch. So we repeat this epoch after epoch until the loss stops decreasing or we have reached the fixed number of iterations. So one complete pass through the entire training dataset is called an epoch. Now let us cover the optimization techniques. Bayesian gradient descent works well for simple models like linear regression because the loss surface is convex, meaning that there is only one global minimum. However, with neural networks usually we have non-convex loss surfaces, that means multiple local minima and saddle points. So while basic gradient descent can still work well, it might not be the most sufficient solution on its own. Momentum adds velocity to gradient descent, so instead of relying only on the current gradient, it also considered past gradients by computing a moving average. Hence it is useful when we are using mini batch for training. It helps reduce oscillations, smooth the updates and converge faster into the direction, and also introduces a parameter beta, typically 0.8 to 0.99, that controls how much past gradients influence the current updates. Adam optimizer is one of the most widely used optimizers when it comes to deep learning, that is neural networks. It combines momentum and adaptive learning rates, so each parameter gets its own step size. This makes Adam very effective for noisy gradients, ideal for mini batch training and highly suitable for deep neural networks. However, for simpler model, it might not be necessary. You can still do with a gradient descent, but in most neural networks, Adam is a default that we go with. Now for learning rate being a critical hyperparameter, we should have an ideal learning rate. Too small learning rate can reduce the convergence and it may cause us not to reach the minimum point even after a lot of epochs. If the learning rate is too large, it can overshoot and again it will lead to instability and failure to converge at the minimum. So we again commonly start with a lower value and we can then increase the value, usually like 0.001, then 0.003, then to 1 decimal ahead, so 0.01 and 0.03 and so on. For learning rate decay, again we can reduce the learning rate over time using exponential step decay or adaptive decay as covered in the linear regression. Exponential decay multiplies the learning rate by a constant factor, so it is smoother for every epoch. Step decay, learning rate decreases at fixed intervals, and adaptive decay reduces learning rate when validation performance stops improving and using a parameter called as patience, that is epochs to wait for. For convergence, we have loss threshold, so we stop when loss reaches a predefined acceptable value. Fixed iterations or iteration count, where we train for a fixed number of epochs. It is simple but may stop too early or too late. Then gradient threshold, we can stop when gradients become very small. We can set a threshold if the gradients are less than the given threshold, it will stop the training process. And early stopping, which is one of the most important specifically for neural networks, it monitors the validation loss and stops when it stops improving. So when the validation loss is no longer improving, we can stop the training process. It helps prevents overfitting, which is one of the major issues with neural networks. And we use a parameter again called patience, where we wait for a specific number of epochs, and if the validation loss does not improve, then we stop the training process. Thank you.